We've spent a lot of time dissecting transformer residual streams with sparse autoencoders. You find a feature for French capital, another for if-then logic, and you start tracing circuits. But there's a growing blind spot. Modern state space models and hybrid recurrent architectures like Mamba 2, RWKV7, and Gated DeltaNet don't just pass vectors through a residual stream. They write memory into a matrix cache using rank 1 outer products. Standard SAEs are built for vectors. They can't directly replace or analyze these matrix writes. This is where WriteSAE comes in. It's a sparse autoencoder designed specifically for the matrix updates written into recurrent state. By matching the geometry of the host architecture, WriteSAE learns rank 1 matrix atoms that can directly replace the model's native writes. The results are striking. On Gated DeltaNet, these atoms beat simply deleting the write on 92.4% of evaluated positions. Even more impressive, a closed-form formula derived from the SAE predicts causal logit shifts with an R2 of 0.98. Let's break down how WriteSAE works, why the architecture match matters, and what this means for steering and interpreting state space models. In Gated DeltaNet, the recurrence writes a rank 1 matrix update for every token. Specifically, each token adds an outer product KTVT $top to the cache state. Later tokens read this state using a query vector. Across a long context, many updates share the same state, and superposition theory suggests these features overlap. The problem for interpretability is shape. A standard SAE trained on the vectorized state has decoder atoms that are flat vectors. To replace a model's rank 1 update, you'd need an outer product. If you try to force a vector atom into a matrix slot, you lose the structural information the downstream layer expects. WriteSAE solves this by constraining the decoder atoms to be rank 1 matrices, $top. This matches the shape of the model's native write primitive exactly. The encoder is also specialized. Instead of a dense linear projection, WriteSAE uses a bilinear encoder. The activation for atom $I is AI equals VI top STWI. This measures the alignment of the current state ST$ with the atom's direction in a way that respects the outer product structure. Training uses a top K sparsity constraint with an auxiliary dead feature loss. The loss minimizes reconstruction MSE plus the dead feature penalty. Crucially, there's no norm matching term during training. The rank 1 decoder costs significantly fewer parameters per atom than a flat dense atom. For a state dimension of 128, a rank 1 decoder uses 256 parameters, whereas a flat dense atom would use 16,384. This efficiency helps, but the real gain is interpretability. A flat atom can mix several native writes into one feature, making causal analysis messy. A rank 1 atom maps 1-to-1 with a single cache event. The validation for WriteSAE goes beyond reconstruction loss. The authors run a replacement test. At a token position where the SAE fires, they swap the model's native write with the SAE's atom, scaled by its activation. They then continue the forward pass and measure the KL divergence between the patched output distribution and the baseline. On Gated DeltaNet, the SAE atom beats deleting the write on 92.4% of evaluated positions. The per atom average win rate is 89.8%. This holds across multiple layers and heads. A random rank 1 atom with the same coefficient performs much worse, confirming that the learned direction is functional, not just a magnitude match. This replacement test reveals 2 distinct populations of atoms. A Gaussian mixture on the cosine similarity to the nearest native write splits the dictionary into registers and bundles. Registers have a high cosine alignment with a specific native write direction. They tend to fire more sparsely and are easier to interpret. For example, one register fires on delimiters next to list numerals, while another fires on proper nouns. Bundles are more diffuse, spreading their direction across many writes. The partition is stable across random seeds, though specific atom identities shift. The most powerful result comes from the logit change formula. The authors derive a closed-form expression for how a rank 1 perturbation changes the logit of a target token. The formula factors into 3 observable quantities: \delta \L \approx GT0 \2T, \Langle WI, QT \Wrangle \Langle VI, W \Wrangle $. Here, G$ is the product of the models for get, gates between the write position and the read position. The second term is the alignment between the atom's read vector WI$ and the query QT$. The third term is the projection of the atom's write vector VI$ onto the output embedding of the target token. This formula predicts measured logit shifts with a median R2 of 0.98 across register atoms. This is incredibly tight. It means we can predict the causal effect of a cache write using a single forward pass, without running expensive counterfactuals. The gate product accounts for the decay of the perturbation over time, and the inner products capture the read-write alignment. This formula also enables targeted interventions. By computing the direction that should maximize a target token's logit, the authors perform generation edits. For tokens initially ranked between 100 and 1000 by the unmodified model, writing this direction into 3 consecutive cache positions at 3 times, the native norm boosts target inclusion from 33.3% to 100%. The median rank shift is positive 517 positions. This demonstrates that the SAE captures the causal direction needed to steer generation. The approach also transfers to larger models. On a held-out QN3, 5-4B model, the same dictionary reduces newline rates by 33% when amplifying features selected by sentence boundary activation. This proves the features capture structural properties of the text, not just local artifacts. Does this work across architectures? The right rule is the key variable. Gated DeltaNet and DeltaNet use rank 1 outer products, and WriteSAE performs excellently. Mamba 2 uses a diagonal state update. WriteSAE adapts by using diagonal atoms. The replacement test still succeeds on Mamba 2, beating deletion on 88.1% of positions, though the alignment is lower. RWKV7 uses rank 2 writes, and the gains are smaller. The logit formula doesn't transfer directly to Mamba 2 because the gate structure differs. The formula yields negative R2 on Mamba 2, indicating the architecture-specific coefficients need adjustment. There are limitations worth noting. Scaling introduces challenges. At the QN3, 5-4B scale, the same SAE recipe fails to produce firing-level effects, with atoms beating deletion only a chance. The 4B SAE achieves better reconstruction MSE, suggesting a decoupling between reconstruction and substitution objectives at larger sizes. This motivates right-aligned training objectives. Additionally, rank 2 atoms provide only marginal gains over rank 1 for RWKV7, likely because the native writes are already dominated by gating decay. WriteSAE highlights a fundamental principle for mechanistic interpretability in state space models. The SAE geometry must match the host architecture's right rule. When you do, you can recover interpretable features, predict causal effects with high fidelity, and perform precise interventions. As these models scale, aligning our tools with their specific state geometries isn't just an optimization. It's necessary to understand how they maintain memory and compute. The code and checkpoints for WriteSAE are available, providing a foundation for exploring cache-level steering in recurrent models. This work opens the door to deeper analysis of fast-weight memory and superposition in the next generation of sequence models.